Good day, everyone. Now, for operations research, we will discuss about simplex algorithm. To recall, this is our first problem example. A pharmaceutical company is currently producing COVID-19 vaccines of two kinds. One is for infected persons, the vaccine 1, and the other is for those who are not infected, vaccine 2. The profit per milligram of the two vaccines is $300 and $250 respectively. The two vaccines are required to be processed in two different machines. The following table shows the available machine hours per day and the time required for each machine to make 1 milligram of vaccine 1 and vaccine 2. Find the quantity of vaccine 1 and 2 that should be produced to maximize the profit. Formulate the linear programming model of this problem. So this is our example of maximization problem. Now let's begin solving the problem with simplex algorithm. 4.1 The algebraic form of the simplex algorithm. From example 1, we got maximize z is equal to 300 x sub 1 plus 250 x sub 2 plus the two slack variables, which is 0 x sub 3 plus 0 x sub 4. They are zeros because they have the coefficient 0 because they do not contribute to the value of the optimal z. Okay, so that is the objective function for example number 1. Now, it is subject to these constraints. 3x sub 1 plus 3x sub 2 plus x sub 3 equals 21. And for the constraint 2, we have 4x sub 1 plus 3x sub 2 plus x sub 4 is equal to 24. You notice that the slack variables are already added in our constraints, which is x sub 3 for constraint 1 and x sub 4 for constraint 2. And of course, the non-negativity constraints is included. So x sub 1, x sub 2, x sub 3, and x sub 4 must be greater than or equal to 0. So for the algebraic form of the simplex algorithm, we start with this step 1. So start by making x sub 3 and x sub 4 as basic variables. What are basic variables again? Those are the variables that we are going to solve in terms of non-basic variables, while non-basic variables are those variables that we let to be equal to 0. Okay, so x sub 1 and x sub 2, which take the value of 0 to get the first solution. X sub 3 is equal to 21 and x sub 4 is equal to 24. So this is its computation calculation. So the first constraint is this: x sub 3 is equal to 21 minus x sub 1 minus x sub 2. So we just transpose 3x sub 1 and 3x sub 2 to the other side of the equation for x sub 3 to remain in the other side. So if we let x sub 1 and x sub 2 is equal to 0, then x sub 3 is equal to 21, right? Next, for the constraint 2, we transpose again the two variables, which is for x sub 1 and 3x sub 2 to the other side to get x sub 4. Then again, we let x sub 1 and x sub 2 equals to 0. Then we found out the value of x sub 4, which is 24, correct? So with those values, we can now substitute to our objective function. So z is equal to 0 plus 300 x sub 1 plus 250 x sub 2. So x sub 1, since x sub 1 and x sub 2 are equal to 0, then the z value must be 0 because x sub 3 and x sub 4, which are slack variables, do not contribute to the value of the optimal z. Okay, so we go now to step number 2. Increase the value of x sub 1 because it has a bigger contribution to the value of c. Okay, why? Because the coefficient or the numerical coefficient of x sub 1 in the objective function is higher, which is 300 higher than the numerical coefficient of x sub 2, which is 250. This is called as enter x sub 1. So that action is called as enter x sub 1. The value to increase x sub 1 should make x sub 3 and or x sub 4 equals to 0 and not negative. So remember that. Thus, the limits for x sub 1 are 7 and 6. Why 7 and 6? Because when you substitute 7 to the first constraint, x sub 3 will become 0. Okay? Because in the first constraint, if x sub 1 is equal to 7 and x sub 2 is equal to 0, then x sub 3 will be 0. So try to substitute it to check it out. Next, for the second constraint, if x sub 1 is equal to 6 and x sub 2 is equal to 0, then x sub 4 will be 0 also. Okay? Now, choose to increase x sub 1 to 6 because if x sub 1 is equal to 7, x sub 0 is equal to 0, then x sub 4 will be negative 4, which is infeasible. Because when we substitute 7 to the second constraint, we will get this negative 4. If x sub 1 is 7 and x sub 2 is 0, we will get x sub 4 as negative 4, which is infeasible. Thus, we will choose the value of 6 to increase x sub 1 to 6 because it does not make x sub 4 negative. Now move on to step number 3. Choose the equation that satisfies step 2 and write the equation in terms of x sub 1. The equation or the constraint 2 satisfy the value of x sub 1 in step number 2 because when we substitute the value of 6 to the second constraint, we get x sub 0 is equal to x sub 4 is equal to 0. Okay? When we substitute 6 to x sub 1 and x sub 2 is equal to 0 in the second constraint, x sub 4 will be equals to 0. So it satisfies. So now we will choose constraint 2. Okay? So we will now write constraint 2 in terms of x sub 1. We will transpose the variables containing x sub 2 and x sub 4 to the other side. And we will simplify to get the first equation. X sub 1 is equal to 6 minus 3 over 4 x sub 2 minus 1 over 4 x sub 4. Now let's go to step number 4. Find the value of x sub 3 by substituting the equation of x sub 1, which we got in the previous equation, in step 3 to the equation containing x sub 3. So the equation containing x sub 3 is the first constraint. Okay, so we write the first constraint, then we substitute x sub 1 with this equation, the equation that we got from step number 3. Then we simplify. So x sub 3 is equal to 3 minus 3 over 4 x sub 2 plus 3 over 4 x sub 4. Okay? Thus, the second solution is x sub 1 is equal to 6 and x sub 3 is equal to 3 if x sub 2 and x sub 4 is equal to 0. Now, how do how did we get that? Okay, so we get the value of x sub 1 by choosing the constant. Okay, the constant in this equation is step number 3, which is 6. So x sub 1 is equal to 6, and we get the value of x sub 3 in the equation in step number 4 because it is the constant here. Because if x sub 2 and x sub 4 are equal to 0, then x the, x sub 1 is equal to 6 and x sub 3 will be equals to 3. So for the step number 5, find the value of z by substituting the equation of x sub 1 and in step 3 to the equation of z. So first, write the equation of z and substitute the equation of x sub 1 we found in step number 3. So it will be, when you simplify it, it will be z is equal to 1800 plus 25 x sub 2 minus 75 x sub 4. Can be further increased by increasing the value of x sub 2. Why? Because it has a positive sign, which has a positive sign but not with x sub 4 because it has a negative sign. So it will be violating the non-negativity sign if we increase that. So step number 6, increase the value of x sub 2. This is called as enter x sub 2. Remember, in step number 1, we enter x sub 1, but here in step 6, we proceed to x sub 2, enter x sub 2, because it has the positive sign. We will not choose the variable with negative sign. So the value to increase x sub 2 should make x sub 1 and or x sub 3 equals to 0 and not negative, because when it becomes negative, it will be infeasible. Thus, the limits for x sub 2 are 8 and 4. Now, how do we get 8 and 4? We just try to make x sub 1 is equal to 0 in the equation we got from step number 3. And we just try to make the value of x sub 3 is equal to 0 in the equation that we got from step number 4. Okay, so we will use the equations we got from step number 3 and step number 4 to find the limits of increasing x sub 2. So for the equation in step number 1, the value of x sub 2 is 8. If x sub 4 is equal to 0, okay, then x sub 1 is equal to 0. Then for the equation in step number 4, the value of x sub 2 must be 4. Because if x sub 4 is equal to 0, then x sub 3 is equal to 0. Now, choose to increase x sub 2 to 4. Because if x sub 2 is equal to 8, then x sub 4 is equal to 0. Then x sub 3 is equal to negative 3, which is infeasible. We got that from by substituting x sub 2 is equal to 8 and x sub 4 is equal to 0 in the equation we got in the step number 4. Okay, so if x sub 2 is equal to 8 here, okay, then x sub 4 is equal to 0, the resulting x sub 3 will be negative 3. So that will be infeasible. So we will choose to increase x sub 2 to 4 because it will not make x sub 1 and x sub 3 be negative. Okay? So step number 7, choose the equation that satisfy step number 6 and write the equation in terms of x sub 2. When you say satisfy, it means that the value of x sub 3 is equal to 0. So here, if the second constraint is the one that we will be choosing, or the equation that we got from step number 4, because it satisfies the value of x sub 2 is equal to 4. Okay, as you notice, this equation that is written here is the equation we got from step number 4. So now we will write that equation in terms of x sub 2. So we will just transpose everything so that x sub 2 will remain in the other side. Okay? So the resulting equation for step number 7 is this. X sub 2 is equal to 4 minus 4 over 3 x sub 3 plus x sub 4. Next, step number 8. Find the value of x sub 1 by substituting the equation of x sub 2 in step 7 to the equation containing x sub 1. So now, we will use the equation that we got from step number 3. Okay? And we will substitute the equation that we got from step number 7. Which we will be substituting in the value of x sub 2. So the resulting equation will be x sub 1 is equal to 3 plus x sub 3 minus x sub 4. Thus, the third solution is x sub 3, x sub 1. Again, thus the third solution is x sub 1 is equal to 3 because we got the constant 3 here in step number 8, and x sub 2 is equal to 4 because we got the constant 4 in step number 7 if we let x sub 3 and x sub 4 is equal to 0. Next, step number 9. Find the value of z by substituting the equation of x sub 2 in step 7 to the equation of z in step 5. So we will write the value of the objective function. The objective function or the equation of z we got from step number 5. So this is the equation in step number 5. We will now substitute x sub 2 that we got from step number 7. So simplifying, we got 7, we got z is equal to 1900 minus 100 over 3 x sub 3 minus 50 x sub 4. Since x sub 3 and x sub 4 in the z equation have negative coefficients, the value of z cannot be increased further. So remember that if the coefficients with the variables have negative signs, we can no longer increase it because it will be infeasible. Thus, z is equal to 1900 is the optimal value, with x sub 1 is equal to 3 and x sub 2 is equal to 4 as the optimal solutions. Now we go to 4.1 tabular form for the maximization. This is under the simplex algorithm. So from example 1, we have this maximization model. So for the step 1, create a simple table for the simplex algorithm. So these are the components of the simplex algorithm table. So this should be create a simplex table. Okay, this is a simplex table. So the first column is for the c sub b. It is the coefficient of basic variables in the objective function, while x sub b is the set of basic variables. They are the variables that we are solving. Next is the objective function value. So we will put the numerical coefficient of the objective function here. Next is the 4 variables. So we have 4 variables including the 2 slacks variables. Next is the right hand side, meaning they are the constant or the value in the right part of the equation. Next is the ratio of RHS or the right hand side value over chosen variables value. So you will learn to compute that later on. Next, objective function value per column, the C sub j, minus Z sub j. It is the sum of the products of each row of C sub b to each row of the four variables per column. Later, you will know how to solve that. So the first, or 1, 2, 3, the third row is the first constraint, and the fourth row is the second constraint. So after creating a simplex table, for step number 2, we begin with x sub 3 and x sub 4 as the basic variable, while x sub 1 and x sub 2 as non-basic variables. Okay, so notice the circled part of the table, which show a matrix with identity property between x sub 3 and x sub 4. It is an identity matrix. Okay, so 1, 0, and 0 and 1. So that's the two slack variables forms the identity matrix. Now for step number 3, choose the column with the highest value of C sub j minus Z sub j and calculate for theta to take the smaller result. Okay, so first the highest value here is 300, and now we will calculate the theta. How do we get theta? So we just divide the value of the right hand side and the value corresponding to the column belonging to 300, because it is the highest value of Cj minus Zj. Okay, so 24 divided by 4 is equal to 6. While on the other hand, 21 will be divided by 3, because 3 is the value belonging to the column of 300. So it is equal to 7. Now, for choosing the theta to enter, we will choose 6 because it has a smaller result. So remember that you always choose the lower result, okay, here in theta, which is 6. So x sub 4 is to be replaced by x sub 1. So the x sub 4 row here, okay, will be replaced by x sub 1 column. Okay, so note, if the denominator in the theta is 0 or negative, do not evaluate it. So since the denominators here in the theta is 3 and 4, we evaluate it because it is not 0 or negative. Next, for the step number 4, add two columns from the previous table to replace x sub 4 and x sub 1 by using the pivot, which is the intersection of x sub 1 and x sub 4, which is 4. Okay, so in our first iteration, we just add some rows for the second iteration so that we will not go back to the previous page to see our first iteration, because we will be using our previous alteration to make the present alteration, which is second iteration. Okay, so now since we choose 6, our pivot element, or the 5 pivot, is 4. Okay, because it is in the intersection of 6 and the highest value of Cj minus Zj. Okay, that is why it is the pivot element, or the pivot. So we will simply write x sub 1 in place of x sub 4, and we will just divide. Okay, we will just divide everything in the previous row, in the row of x sub 4 in the first iteration, with the pivot element, or the pivot, which is 4. So 4 divided by 4 is 1. 3 divided by 4 is 3/4. 0 divided by 4 is 0. 1 divided by 4 is 1/4. And 24 divided by 4 is 6. Now, we will write 300 here because it is the value of, or the numerical value of x sub 1. Remember in our objective function 300 x sub 1, so we write here the 300. Next instruction is step number 4. Rewrite row x sub 3 by making an identity matrix between x sub 1 and x sub 3, just like the identity matrix between x sub 3 and x sub 4 in step number 2. So to do that, get the difference between the previous row value of x sub 3 and the product of 3 and x sub 1 row value. So we now do that. So why do we choose the value 3? Because when we multiply 3 by the values in the x sub 1 row in our second iteration, we will get an identity matrix. Okay, so 1 times 3 minus 3, okay, 3 minus 3, okay, the product we get from multiplying the number we choose in the with each element in the x sub 1 row, we will subtract it from the value for each element in x sub 3 to rewrite the new x sub 3 row. Okay, so we choose 3. So 3 times 1 is 3. Now 3 minus 3 is equal to 0. Okay, so always remember, we always make an identity matrix between the variables under x sub b, which is for the second iteration x sub 3 and x sub 1. So whatever the variables here, we will make identity matrix between them to proceed with our iteration. Okay, so next, 3 times 3 over 4 is what? Is 9 over 4. Okay, now we got 9 over 4 here, so we will subtract it from its corresponding value or element of x sub 3. So 3 minus 9 over 4 is equal to 3/4. That's why it is 3/4. You get that? So next, 0. 0 times 3 is equal to 0. So 1 minus 0 is 1. Now you notice that we have an identity matrix between x sub 3 and x sub 1. It's 0 and 1 and 1 and 0. Okay? So that thing is the step we use when proceeding with iterations. Okay? So for this column, 1/4 times 3 is equal to 3/4. Now 0 minus 3/4 is equal to negative 3/4. Okay? Now 6 times 3 is 18. So 21 minus 18 is equal to 3. Alright, do you get that? Now we have written the new x sub 3 row. Now, how do we get the value of cj minus zj here? Okay, why this is 0? So to get that, we'll just multiply the value here in c sub b 0 times 0. So it is 0. Next, 300 times 1 is equals to 300. So 0 plus 300, okay, we have 300. Now that 300, we will subtract it from the value here, okay, the value in the uppermost column, which is 300. So 300 minus 300 is equal to 0, right? Next, for the next column, 0 times 3/4 is equal to 0. Now 300 times 3/4, it will be 225. Okay, so 0 plus 225 is equal to 225. Now we will subtract the 225 to 250. So 250 minus 225, so 250 minus 225 is equal to 25. That's why we have 25 here. Okay, next, 0 times 1 is 0. 300 times 0 is 0. So 0 plus 0 is equal to 0. Okay, Now we will subtract that from the value here. So 0 minus 0 is equal to 0. Okay? Next, 0 multiply negative 3/4 is equal to 0. Then 300 multiplied by times 1/4 is equal to 75. So 0 plus 75 is equal to 75. Now we will subtract it to 0, the value here. So 0 minus 75 is equal to negative 75. Alright? Next. How do we get the value 1,800 here? So we simply multiply 0 and 3, so it is 0. 300 times 6 is 1,800. So 0 plus 1,800 is equal to 1,800. Okay? Next, for the step number 5, again, we will choose to enter the variable with the highest positive value of c sub j minus z sub j, which is x sub 2, right? Because, going back here, the highest value in the last row is 25. Okay? So it belongs to x sub 2, right? Then, to find what row should be replaced, solve for theta and choose the smallest positive value, which is 4. Okay? So, how do we get 4? Here. So, in the intersection of x sub 2 column and the rows of x sub 3 and x sub 1, we solve theta. Okay? So, 3/4 divided by, or 3, okay? So, we get theta here for x sub 3 row by dividing the value of RHS, which is 3. That's why it is 3 here. So, 3, the numerator divided by the intersection of x sub 2 and x sub 3, which is 3/4. So, 3 divided by 3/4 is equal to 4. Next, for the x sub 1 row, the numerator is 6 because it is the value in the RHS. So 6 divided by the intersection of x sub 2 and x sub 1, which is 3/4, is equal to 8. Okay? So now we will choose to enter 4 because it has the smallest positive value of theta. So step number 6. Do step 4. So we will just repeat this step 4 for the third iteration. So the pivot now is 3/4 and the pivot row is x sub 3. Okay, so we go now to the third iteration, the second and third. Okay, because we will making second iteration as our reference for the third iteration. Okay, so the pivot element now, or the pivot is 3/4, okay, because it belongs to the row of the smallest theta and it belongs to x sub 2 column. Okay, so we will just simply divide all the elements in this x sub 3 row by the pivot element, which is 3/4. So 0 divided by 3/4 is 0. 3/4 divided by 3/4 is 1. 1 divided by 3/4 is 4/3. Negative 3/4 divided by 3/4 is negative 1. 3 divided by 3/4 is 4. And we will replace x sub 3 by x sub 2. And of course, we will put here under c sub b the value of the numerical coefficient of x sub 2 in our objective function, which is 250. Right? Now, we will make a identity matrix between x sub 2 and x sub 1 because they are the variables that we are solving, or they are the variables that belong to x sub b. So, what number we can use to make a identity matrix between them. So it must be 3/4. Why? Because when we multiply 3/4 by the value here, okay, the value 0, so 0 times 3/4 is equal to 0. Now we will subtract 0 from the previous value of x sub 1. So 1 minus 0 is equal to 1. Okay. Next, the value here in the next column is 1. So we will multiply 3/4 by 1. So 1 times 3/4 is 3/4. Now, we will subtract the previous value here of x sub 1 in the previous iteration. So 3/4 minus 3/4 is equal to 0. Now we have, now we have an identity matrix between x sub 2 and x sub 1. Do you get it? 0 and 1 and 1 and 0. Okay? So, we will just continue it by using 3/4. So, 4/3 times 3/4 is equal to 1. So, we will just subtract 1 to 0. So, 0 minus 1 is negative 1. Next column, negative 1 times 3/4 is equal to negative 3/4. So, we will just subtract negative 3/4 to the previous element, which is 1/4. So 1/4 minus negative 3/4, it will become plus or positive. So 1/4 plus 3/4 is equal to 4/4, which is equal to 1. Okay? Next, we multiply 4 by 3/4. So 3/4 times 4 is equal to 3. That's why we minus 3 to 6. So 6 minus 3 is equal to 3. Okay, do you get it? How do we get this? And now, we will solve for the values of c sub j minus cj here. So for the first column, so 250 times 0 is equal to 0. So 300 times 1 is equal to 300. So 0 plus 300 is equal to 300. So we will just subtract. For this column, the value is 300. So 300 minus 300 equals to 0. Next, for the next column, 250 times 1 is equal to 250. So 300 times 0 is equal to 0. So 250 plus 0 is 250. And the value of the numerical coefficient under this column is 250. So 250 minus 250 is 0. Okay? Next, 250 times 4/3, it will become 1000 over 3. Next, 300 times negative 1 is equal to negative 300. So we will now add 1000 over 3 and negative 300. So 1000 over 3 minus negative 300. So the answer is 100 over 3. Now, the value of the numerical coefficient under this column, the value in the objective function is 0. Okay, so we will subtract 100 over 3 to 0. So 0 minus 100 over 3 is equal to negative 100 over 3. Okay, so next, negative 1 or 250 times negative 1 is equal to negative 250. Next, 300 times 1 is equal to 300. So we will now add them. Negative 250 plus positive 300 is positive 50. So the value of numerical coefficient under this column is 0. Okay, the value in the objective function. So we will now subtract. So 0 minus 50 is negative 50. That's why it is negative 50 here. Right? Now, since all the values in c sub j minus z sub j are 0 and negative values, the iteration ends here because it cannot longer be increased. This is the optimal solution and value. So the optimal solution for x sub 2 is equal to 4, then x sub 1 is equal to 3, with the optimal z value of 1900. Right? Since the value of basic variables x sub 1 and x sub 2 are both 0 and the values of non-basic variables x sub 3 and x sub 4 are both negative values, no variable can be entered anymore. Thus, the algorithm terminates giving the best solution. Okay? Next, 4.2, we have the tabular form for minimization. To recall, this is the example number 2 problem. A college department has two groups of faculty, G1 and G2, who have assigned members to make learning modules of major and minor subjects for students who have limited or no internet access. The college head sets a target of at least 4 and 10 modules of major and minor subjects per week respectively. The labor costs are 5,000 PHP and 6,000 PHP in making G1 and G2 modules per day, respectively. On a day, G1 accomplishes 1 and 5 major and minor subject modules, while G2 accomplish 1 and 2 major and minor subject modules, respectively. How many days per week should each group work to meet the target most economically? Formulate the linear programming model of this problem. So from that problem, we formulate our linear programming model, which is to minimize the objective function z is equal to 5,000 x sub 1 plus 6,000 x sub 2 plus the slack variables 0 x sub 3 plus 0 x sub 4, subject to the following constraints: x sub 1 plus x sub 2 minus x sub 3, since this is a minimization. The slack variables are negative, equals 4. 5x sub 1 plus 2x sub 2 minus x sub 4 is equal to 10. So with the non-negativity constraint, x sub 1, x sub 2, x sub 3, and x sub 4 should be greater than or equal to 0. So those variables should not be negative. Otherwise, it will be infeasible. So next, for step number 1, for the tabular form of the minimization, step 1. To start a simplex minimization table, add artificial variables a sub 1 and a sub 2 because of the negative sign of slack variables x sub 3 and x sub 4. So here, in minimization, after adding our slack variables, we will introduce another variable which is called as artificial variables. So we will add them to offset the negative sign of the slack variables in our constraint. Okay? So just like the slack variables, artificial variables do not mean anything from the value of z. We just use the numerical coefficient m, okay, that stands for a very big value, okay, a very big value, but it doesn't contribute to the z value. We just use it to produce or obtain the basic feasible solution. Okay? So as you notice, in the constraint, we just add a sub 1 for the first constraint and a sub 2 for the second constraint as the artificial variables. So the m here is, or the big M, is a notation used to represent a very large positive value that tends to infinity. Okay? So we just consider it as a very large positive value. So in step number 2, make a simple table and multiply the objective function values with -1. So we make our simplex table. Okay, so it should be simplex make a simplex table. Okay, after we make a simplex table, we multiply all the coefficients of the objective function with -1. That's why it becomes -5,000, -6,000, 0, 0, and -m, -m. Notice that there is a matrix with identity property between a sub 1 and a sub 2 that will serve as a starting solution. Okay, so between a sub 1 and a sub 2, because it is under x sub b, okay, so there is a identity property. Okay, so under this column a sub 1, column a sub 2, there is 1, 0, and 0, 1. So whenever we see an identity property, we can start our iteration from there. Okay, it will be as a starting solution. So note, just leave C sub j minus zj value of RHS to 3 dash, okay, until there is no artificial variable in the solution. So as long as there is an artificial variable in the solution, we just make RHS is equal to 3 dash. Now, we choose the highest positive value, okay, of C sub j minus z sub j. So the highest positive value here is 6m minus 5,000. Okay, so it is under x sub 1 column. So now we will compute the theta. So the value of RHS divided by the corresponding element in the x sub 1 column. So 4 divided by 1 is equal to 4. Then 10 divided by 5 is equal to 2. So now we will choose uh, the row a sub 2 because it has a smaller theta. So we will replace a sub 2 by x sub 1. So step 3, we choose to enter the variable with the highest positive value. Okay, so it is 6m minus 5,000, and we will replace a sub 2 because it has a smaller value of theta. So the pivot here, or the pivot element here, is 5 because it is the intersection between x sub 1 with the highest positive value of cj minus zj, and a sub 2, which is the smallest theta. Okay, so it will be the pivot element 5. So, and the pivot row is a sub 2. So we will rewrite the pivot row in terms of x sub 1 by making an identity matrix between x sub 1 and a sub 1. Okay, because for the second iteration, the values under x sub b are a sub 1 and x sub 1. Okay, so we will make an identity matrix between them. So we will just copy the value of the numerical coefficient of a sub 1, okay, a sub 1 column in the row or in the objective function value. So the value for a sub 1 is -m. Okay, then for x sub 1 it is -5,000. Okay, we will just look at this uppermost row, the value that corresponds to it. Okay, we will put that under C sub B. So next, we will divide all the elements in the first iteration along a sub 2 row with the pivot element, which is 5. So 5 divided by 5 is 1, and 2 divided by 5 is 2/5. 0 divided by 5 is 0. -1 divided by 5 is -1/5. 0 divided by 5 is 0. 1 divided by 5 is 1/5. 10 divided by 5 is 2. Alright, so now we replace a sub 2 row with x sub 1 row in our second iteration. Okay, now we will rewrite a sub 1, okay, by making an identity matrix between a sub 1 and x sub 1 because they are the variables under x sub b. Okay, so they are the basic variables. They are the one we are solving. So to do that, what should be uh, the value that we will use to multiply each value of each value or each element along x sub 1 and subtract it with the previous elements along a sub 1, so that the value that will be here is equal to 0, because we are going to make an identity property. Okay, so it should be equal to 1. So the value that we choose is 1. Okay, because 1 times 1, okay, 1 times the first element in x sub 1 row, which is 1, is equal to 1. Okay, so that one we will subtract to the value, the element 1 from the previous row of a sub 1. So 1 minus 1 is equal to 0. Okay, so that's it. So that we can make an identity matrix between them, a sub 1 and x sub 1. So next, 2/5 times 1 is equal to 2/5. Now, we will minus 1 minus 2/5 is equal to 3/5. Okay, next, 0 times 1 is equal to 0. So negative 1 minus 0 is negative 1. So next, negative 1/5 times 1 is negative 1/5. So 0 minus negative 1/5 is equal to positive 1/5. Next, 0 times 1 is 0. So 1 minus 0 is 1. Next, 1/5 times 1 is 1/5. So 0 minus 1/5 is negative 1/5. Next, 2 times 1 is 2. So 4 minus 2 is 2. Okay, do you get it? So now we will solve for the values of Cj minus Zj for each column. So for the first column, which is under x sub 1, we multiply negative m multiplied by 0 is 0. Negative 5,000 multiplied by 1 is negative 5,000. So now 0 plus negative 5,000 is negative 5,000. That negative 5,000 we will use to subtract to the values corresponding to x sub 1 in this column, which is negative 5,000. So negative 5,000 minus negative 5,000, so it will be plus 5,000. So negative 5,000 plus, because of double negative, so negative 5,000 plus 5,000 is equal to 0. Now for the column under x sub 2, we will compute for the Cj minus Zj. So negative m multiplied by 3/5 is negative 3/5 m. Then negative 5,000 multiplied by 2/5 is equal to negative 2,000. So negative 3/5 m minus or plus negative 2,000 is equal to negative 3/5 m minus 2,000. So that figure we will subtract to the given value or the given numerical value of under x sub 2, which is negative 6,000. Okay, if we look to the top, it is negative 6,000. So it will be negative 6,000 minus negative 3/5 m minus negative 2,000. So the result will be positive 3/5 m minus 4,000. Okay, next column, negative m times negative 1 is equal to positive m. Negative 5,000 times 0 is 0. So positive m plus 0 is positive m. Now, the value corresponding to that column is 0. So 0 minus m, 0 minus positive m is equals to negative m. That's why it is negative m here. Okay, so next, negative m multiplied by 1 over 5 is negative 1/5. And negative 5,000 multiplied by negative 1/5 is equal to 1,000. So negative 1/5 plus positive 1,000. So we will now subtract that from this, which is 0. So 0 minus negative 1/5 plus 1,000 is equal to 1/5 m minus 1,000. Okay? So next, negative m times 1 is negative m. Negative 5,000 times 0 is 0. So negative m plus 0 is negative m. So now we will subtract it. So negative m minus negative m is equal to 0. That is why it is 0 here. Next, negative m multiplied by negative 1 over 5 is equal to positive 1/5 m. And negative 5,000 multiplied by 1/5 is equal to negative 1,000. So, positive 1/5 m plus negative 1,000 is equal to 1/5 m minus 1,000. So, we will use that to subtract from this. So, negative m minus positive 1/5 m minus 1,000. So, the result will be negative 6 over 6 6/5 m plus 1,000. Okay? So, that is the second iteration. So, we will just leave the value of the optimal z here as dash, okay? Because there is a variable m in cj z minus zj, okay? So it will be dash. So step number 4, again, we choose the variable with the highest positive value of cj minus zj, which is 3/5 m minus 4,000. Okay, it is the highest positive value here, right? 3/5 m minus 4,000. And replace a sub 1 because it has a smaller value of theta. Okay, so what will be its theta? So under x sub 2, because it has the highest value of 3 of cj minus zj, and we will just uh, compute the theta from that. Okay, so to compute the theta from that, we go to the second iteration to compute the theta. Okay, so the intersection or the highest, okay, the highest value of cj minus zj here is 3 over 3/5 m minus 400. So we will divide the value of RHS here by the elements under this column of the highest value of cj minus zj. Okay, so 2 divided by 3/5 is equal to 10 over 3 or 10/3. Then 2 divided by 2/5 is equal to 5. Okay, so now which is smaller, 10/3 or 5? So the smaller one is 10/3. Okay, so we will now choose this row a sub 1. We will replace a sub 1 by x sub 2 because it has the highest value of cj minus zj. As you notice, as we go to our third iteration, a sub 1 is replaced by x sub 2. Okay, and to rewrite the pivot row, which is a sub 1 in terms of x sub 2, we will just divide all the elements from the previous row in the second iteration, previous a sub 1, with the pivot element, okay, with the pivot element. So what is the pivot element here? The pivot element is 3/5. Why it is the pivot element? Because it lies in the intersection between the highest positive value of cj minus zj and the lowest value of theta. Okay, so it is in the intersection. So to rewrite it, we divide 0 divided by 3/5 is equal to 0. 3/5 divided by 3/5 is equal to 1. Negative 1 divided by 3/5 is equal to negative 5/3. 1/5 divided by 3/5 is equal to 1/3. 1 divided by 3/5 is equal to 5/3. Negative 1/5 divided by 3/5 is equal to negative 1/3. 2 divided by 3/5 is equal to 10/3. Alright? So we will put negative 6,000 here under C sub B because it is the value, the numerical value associated with x sub 2, negative 6,000. Okay? Now, we will have to make an identity matrix between x sub 2 and x sub 1. Okay? To start the to continue our iteration. So, what number that we can use in order for us to make an identity matrix? So, to make an identity matrix between x sub 2 and x sub 1, we should make the value of the first and second elements under x sub 1, 1 and 0. Okay? So, to do that, we can use 2/5. Okay? We can use the value of 2/5. Why? Because when we multiply 2/5 and 1, so 1 times 2/5 is equal to 2/5. Next, we will subtract it from the previous value, so of x sub 1 in the iteration 2. So 2/5 minus 2/5 is equal to 0. That is why it is 0 here. And for the first one, 0 times 2/5 is equal to 0. Okay, so 1 minus 0 is equal to 1. Okay, so we have now our identity matrix. Okay, so next, negative 3/5 times 2/5 is equal to negative 2/3. Okay, so 0, the previous value, 0 minus negative 2/3 is equal to positive 2/3. Okay, so negative 1/3, okay, 1/3 times 2/5 is equal to positive 2/15. Okay, so the previous value is negative 1/5. So negative 1/5 minus 2/15 is equal to negative 1/3. That is why it is negative 1/3 here. Okay, so next, 5/3 times 2/5 is equal to 2/3. So the previous value is 0. So 0 minus 2/3 is equal to negative 2/3. That is why it is negative 2/3 here. Okay, so next, negative 1/3 times 2/5, it is negative 2/15. Okay, so negative or positive 1/5 is the previous value. So positive 1/5 minus 2/15 is equal to positive 1/3. That is why it is positive 1/3 here. Okay, so next, 10/3 or 10/3 times 2/5 is equal to 4/3. Okay, so the previous value is 2, so 2 minus 4/3 is equal to 2/3. Okay, so now we can compute the Cj minus Zj. Okay, so for the first column under x sub 1, 6,000 multiplied by 0 is 0. Negative 5,000 multiplied by 1 is negative 5,000. So we will just subtract that negative 5,000 because 0 plus negative 5,000 is negative 5,000. We will subtract it to the value of x sub 1 here, associated with x sub 1, which is negative 5,000. Okay, so it will be negative 5,000 minus negative 5,000. So it will be 0. Okay, next column under x sub 2. So negative 6,000 times 1 is equal to negative 6,000. Next, negative 5,000 times 0 is 0. So negative 6,000 plus 0 is negative 6,000. So the value of x sub 2 here, the numerical value associated with x sub 2 is negative 6,000. Okay, so negative 6,000 minus negative 6,000. So it will be 0. So now we will get the Cj minus Zj of x sub 3 column. Okay, so negative 6,000 times negative 5 thirds is equal to positive 10,000. Negative 5,000 times 2 thirds is equal to negative 10,000 over 3. So positive 10,000 plus negative 10,000 over 3 is equal to positive 20,000 over 3. Now we will use it to subtract to the numerical coefficient of x sub 3, which is 0 in this column. So 0 minus 20,000 over 3 is negative 20,000 over 3. That is why it is negative 20,000 over 3 here. Okay? So next, in the column of x sub 4, negative 6,000 times 1 thirds is equal to negative 2,000. Negative 5,000 times negative 1 thirds is equal to positive 5,000 over 3. So now, negative 2,000 plus 5,000 over 3 is equal to 1,000 over 3. So we will use it to subtract again in the numerical coefficient of x sub 4, which is 0. So 0 minus 1,000 over 3 is 0 minus negative 1,000 over 3 is positive 1,000 over 3. That's why it is positive 1,000 over 3 here. Okay? So next, under a sub 1 column, so negative 6,000 times 5 thirds is equal to negative 10,000. 5,000 times negative 5,000 times negative 2 thirds is equal to positive 10,000 over 3. So negative 2,000 plus 10,000 over 3 is equal to negative 20,000 over 3. So we will use it again to minus or to subtract the numerical coefficient of a sub 1, which is negative m. So negative m minus negative 20,000 over 3 is equal to negative m plus 20,000 over 3. That's why it is written here. Okay? So next, negative 6,000 times negative 1 thirds is equal to positive 2,000. Then, negative 5,000 times 1 thirds is equal to negative 5,000 over 3. So, positive 2,000 plus negative 5,000 over 3 is equal to 1,000 over 3. So, we will use it again to subtract the numerical coefficient of a sub 2, which is negative m. So, negative m minus 1,000 over 3 is equal to negative m minus 1,000 over 3. Okay? So now we will leave the optimal value z as blank because it has the value m again in the zj minus zj here. Okay? So now we can solve for the theta. Okay? Okay, to solve the theta first, find the highest positive value in the Cj minus Cj. Okay, so the highest positive value is 1,000 over 3. It is under the column of x sub 4. Okay, so we will use the elements under x sub 4 to compute for our theta. Okay, so 10 over 3 divided by 1 thirds. Okay, because it is the element under x sub 4. So 10 over 3 divided by 1 thirds is equal to 10. Next, 2 thirds divided by negative 1 thirds is equal to negative 2. Okay? So now, we will select positive 10. Okay? Because we will not select negative, for it is infeasible. Okay, so we will select x sub 2 row, okay, because it has the smallest positive value. We will not select negative, okay. So x sub 2 will be replaced by x sub 4 this time, okay. So step 5, again, choose the variable with the highest positive value, which is 1000 over 3, and replace x sub 2 because it has the only positive value of theta. The pivot now, or the pivot element, is 1/3, okay? Because it lies in the intersection of the highest positive value Cj minus Zj and the smallest positive value, or the only positive value of theta. Okay? So now we will rewrite row the pivot row in terms of x sub 4. Okay, so let's go to the third and fourth iteration. Okay, so for the fourth iteration, you notice that we have replaced x sub 2 row with x sub 4. Okay, so how did we do that again? Okay, so uh, since our pivot element here is uh, 1/3, okay, so 1/3 is our pivot elements, we will divide all the elements in the previous row of x sub 2, which is in the third iteration, by it. So 0 divided by 1/3 is equal to 0. 1 divided by 1/3 is equal to 3. Negative 5/3 divided by 1/3 is equal to negative 5. 1/3 divided by 1/3 is equal to 1. 5/3 divided by 1/3 is equal to 5. Negative 1/3 divided by 1/3 is equal to negative 1. Okay? 10/3 divided by 1/3 is equal to positive 10. Okay? So now, we have to make an identity matrix between x sub 4 and x sub 1 because they are the one who are written here. Okay? In the x sub b column. Okay? So, what number we can use to make the value of x sub 1 here in the column of x sub 1, in the row of x sub 1, to become 1, okay, as well as uh, the value of x sub 1, the row x sub 1 here under the column x sub 4, to become 0, to have an identity matrix. Okay, so we should use negative 1/3. Why? So look at the column of x sub 4. Okay, so the value of the row value of the uh, element here in x sub 1 should be 0. So when we multiply negative 1/3 in the value of x sub 4, which is 1, so 1 times negative 1/3 is equal to negative 1/3. So now we will use it to subtract in the previous value of the row x sub 1, which is negative 1/3. Okay, so negative 1/3 minus negative 1/3 is equal to 0. Okay, so now we will use negative 1/3 to multiply. Okay, in the value of row value of x sub 4. Okay, so 0 times negative 1/3 is equal to 0. So 1 minus 0 is equal to 1. Okay, next, 3 times negative 1/3 is equal to negative 1. So 0 minus negative 1 is equal to 1. Okay, next, negative 5/3 times negative 1/3 is equal to positive 5/3. Okay, so 2/3 minus 5/3 is equal to negative 1. Okay, then we have solved x sub 4 column. Okay, so let's go to uh, a sub 1 column. Next, 5 times negative 1/3 is equal to negative 5/3. So negative 2/3 minus negative 5/3 is equal to positive 1. Okay, next, negative 1 times negative 1/3 is equal to positive 1/3. Okay, so 1/3 minus 1/3 is 0. Okay, so 10 times negative 1/3 is equal to negative 10 over 3 or negative 10/3. So 2/3 minus negative 10/3 is equal to 4. Okay? So now we will compute the Cj minus Zj of fourth iteration. So 0 is the value of the numerical coefficient of x sub 4 in our objective function. That is why 0 is written here in the C sub b column. Okay, so 0 times 0 is equal to 0. Negative 5,000 times 1 is equal to negative 5,000. So we will use it to subtract again. So 0 plus negative 5,000 is negative 5,000. We will use it to subtract the numerical coefficient of this column, which is x sub 1. The numerical coefficient here is negative 5,000. So negative 5,000 minus negative 5,000 is equal to 0. Next column, x sub 2 column. 0 times 3 is 0. So negative 5,000 times 1 is negative 5,000. So 0 plus negative 5,000 is negative 5,000. Okay? So since the value of C sub b in x sub 4 row is 0, we will not compute it anymore, okay? Because the value that matters is the value under x sub 1, okay? X sub 1 row. So negative 5,000. So the numerical coefficient of x sub 2 under this row is negative 6,000. So negative 6,000 minus negative 5,000 is equal to negative 1,000. Okay? So next, negative 5,000 times negative 1 is equal to positive 5,000. So the numerical coefficient here under x sub 3 is 0. So 0 minus 5,000 is equal to negative 5,000. Okay? Next, negative 5,000 times 0 is 0. So 0 minus 0 is 0. Okay? Next, negative 5,000 times 5, times 1, okay, it will be negative 5,000. So the numerical coefficient here under a sub 1 is negative m. So negative m minus negative 5,000 is negative m plus 5,000. So next, negative 5,000 times 0 is 0. So the numerical coefficient here is negative m. 0 minus negative m minus 0 is negative m. So now we notice that all the cj minus zj is equal to 0 and negative. So our iteration ends here. So in a minimization method, just multiply negative 1 to the final optimal value to make it positive. Okay? Since the value of basic variables x sub 1 and x sub 4 are both 0, okay, so it is under the column of x sub 1 and x sub 4, you notice that it is 0 and in the row along the row cj minus zj. And the values of non-basic variables x sub 2, x sub 3 are both negative values. No variable can be entered anymore. Okay, so thus the algorithm terminates, giving the best solution x sub 1 is equal to 4 and x sub 4 is equals to 10, with the best optimal value of the objective function z is equal to 20,000. Why it is 20,000? Because when you multiply 0 and then it's 0, it is zeroed. And when you multiply negative 5,000 and 4, it is negative 20,000. Now, in minimization method, you will just multiply negative 1 to make it positive. Okay? It will be 20,000. Now let's go to 4.3 unboundedness. Okay, so for the example number 3, suppose we have this linear programming model, okay, maximization model. So maximize z is equal to 10 x sub 1 plus 9 x sub 2. That is the objective function. Subject to x sub 1 minus x sub 2 less than or equal to 5. Then 4x sub 1 less than or equal to 24 with the non-negativity constraint x sub 1, x sub 2 greater than or equal to 0. So first, we will add slack variables to them. As you notice, we have add them x sub 3 and x sub 4. Okay, since this is a maximization, the slack variables in the constraints are positive. Okay, so let's put them in a simplex table. Okay, this is the first iteration. Okay, so x sub 3 and x sub 4 as our basic variables because we have the uh, identity matrix between them. Okay, as you notice, 1 0 and 0 1. So we will find, or we will choose the highest positive value again of Cj minus Zj, which is 10. Okay, then we will compute for the theta using the RHS value over the value under the column of the highest positive value of Cj minus Zj. Okay, so 5 divided by 1 is 5. 24 divided by 4 is 6. So we will choose the smallest or smaller positive value, which is 5 here. So x sub 3 will be replaced by x sub 1. Okay? So in our second iteration, you notice that x sub 3 is replaced by x sub 1. Okay? So we will rewrite that row by uh, dividing all the elements in the previous row, which is in the first iteration of x in the row x sub 3 with the pivot element. The pivot element is 1 because it lies in the intersection of the highest positive value of Cj minus Zj and the lowest positive value of theta. Okay, so 1 divided by all the elements makes it as is. Okay, so we just copy all of the elements of the previous row in x sub 3 row in the first iteration to the second iteration of x sub 1 row. Okay, next, x sub 4, we have to make an identity matrix between x sub 1 and x sub 4 because they are the one who are written here in x sub b, or the basic variables. Okay, so what number can we choose to do that? So it should be 4, okay, because the value here of x sub 4 should be 0, 0. So when we multiply in the column of x sub 1, the value of 1, okay, so 1 times 4 is 4. So we will subtract, so the previous value in the of x sub 4, row x sub 4 is 4. So 4 minus 4 is equal to 0. That is why it is 0 here. Okay, so next, negative 1 times 4 is negative 4. Okay, so 0, the previous value, minus negative 4 is equal to positive 4. Okay, next, 1 times 4 is 4. So 0, the previous value, minus 4 is equal to negative 4. Okay, so 0 times 4 is 0. So 1, the previous value, minus 0 is 1. Next, 5 times 4 is 20. So the previous value is 24. 24 minus 20 is 4. Okay? So to compute the Cj minus Zj, so we will just multiply it. So 10 is the numerical coefficient value of x sub 1. Okay, that is why 10 here. 10 is written here, and 0 is the numerical coefficient of x sub 4. That's why it is written here, 0. So 10 times 1 is 10. 0 times 0 is 0. Okay, so 10 plus 0 is 10. Okay, now we will subtract it from the numerical coefficient of this column, which is x sub 1. So the numerical coefficient is 10. 10 minus 10 is 0. Okay, so next, in the column of x sub 2, 10 times negative 1 is negative 10. 0 times 4 is 0. Oh, since the numerical coefficient of x sub 4 is 0, we will not compute it anymore. We will just compute the value of x sub 1 because it has a numerical coefficient of 10. Okay, so negative 1 times 10 is negative 10. So we will subtract it from the value of x sub 2. So what is the value of x sub 2? Here, the column is 9 is the value. So negative 10. So 9 minus negative 10 is equal to positive 19. Okay, so next, 10 times 1 is 10. So 0 minus 10 is negative 10. Okay, next, 0 times 10 is 0. So 0 minus 0 is 0. Okay, so next, 10 times 5 is 50. So we have 50 here in the RHS. Now, we will choose for the third iteration, we will choose the highest positive value of Cj minus Zj of second iteration, which is 19. So it lies in the column of x sub 2. And we will compute the theta. So 5 divided by negative 1. So remember, if we have a negative denominator, we will not evaluate it because it is infeasible. So we will evaluate the second one. 4 divided by 4 is equal to 1. So we will choose to replace x sub 4 by x sub 2. Okay? So for the third iteration, x sub 4 was replaced by x sub 2. And the pivot row, okay, so what is the pivot row here? The pivot row is 4 because it is in the intersection of our conditions, okay? 4. Now to rewrite everything, we will just divide the previous elements with 4. Okay, so first, 0 divided by 4 is 0. So 4 divided by 4 is 1. Okay, so negative 4 divided by 4 is negative 1. So 1 divided by 4 is 1/4. So 4 divided by 4 is 1. Okay, so we have rewritten the the row, okay, the pivot row. Next is we will make an identity matrix between x sub 1 and x sub 2. So what is the number that we can use to do that? So the value of x sub 1 here should be 1, okay? And the value of x sub 1 in the x sub 3 column should be 0. Okay, the value of x sub 1 in the x sub 2 column should be 0, okay? So to have a identity matrix, so what number can we use? So let's think about that. So it should be negative 1 to make it 0, okay? So when we multiply negative 1 with the values of x sub 2 row here, so negative 1 times 0 is 0. So the previous value is 0, or the previous value is 1, so 1 minus 0 is equal to 1. Okay, so next, negative 1 times positive 1 is negative 1. Okay, so the previous value is negative 1. So negative 1 minus negative 1 is equal to 0. Okay, that's why it is 0 here. So next, negative 1 times negative 1 is positive 1. So the previous value is 1. So 1 minus 1 is 0. That is why 0 here. Next, negative 1 times 1/4 is negative 1/4. So the previous value is 0. So 0 minus negative 1/4 is positive 1/4. Okay? So next, negative 1 times 1 is negative 1. So the previous value is 5. So 5 minus negative 1 is positive 6. Okay? So we can now compute for the Cj minus Zj. Okay? So under the x sub 1 column, 10 times 1 is 10. 9 times 0 is 0. So the numerical value here is 10. So 10 minus 10 is equal to 0. Next, 10 times 0 is 0. 9 times 1 is 1. So the numerical value here is 9. So 9 minus 9 is 0. Okay, next, under x sub 3 column, 10 times 0 is 0. 9 times negative 1 is negative 9. So the numerical coefficient here is 0 in the top. So 0 minus negative 9 is positive 9. Next, 10 times 1/4 is equal to 5 halves. Okay? So 9 times 1/4 is equal to 9/4. Okay? So 5 halves plus 9/4 is equal to positive 19 over 4. So the numerical coefficient here is 0. So 0 minus 19 over 4 is negative 19 over 4. Okay? So we will now compute the optimal value. 10 times 6 is 60. 9 times 1 is 9. So 60 plus 9 is 69. So since one denominator, okay, since one denominator in theta calculation is 0 and the other is negative, because when we calculate the theta here under the third iteration, we will get 0 and negative. So the highest positive value of Cj minus Zj is 9, okay? So we will use that as our denominator. So 6 divided by 0 will be undefined, and 1 divided by negative 1 will be infeasible. Therefore, there will be no living variable and the algorithm terminates, showing unboundedness. Okay? What do you mean by unboundedness? So there are no boundaries. So the solutions we are trying to find out tends to go to infinity. Okay? The following graph shows that the feasible region has no enclosed boundary in extending to infinity. So when we graph it, it will look like this. So this is the case of unboundedness. Okay. Next, 4.4 infeasibility. So example number 3. Maximize z is equal to 10 sub x sub 1 plus 9 x sub 2, subject to these constraints. X sub 1 plus x sub 2 less than or equal to 5. Then for x sub 1 greater than or equal to 24. With the non-negativity constraint again as x sub 1 and x sub 2 greater than or equal to 0. So adding the slacks variable, you notice that in the second constraint, we have a negative slack variable which is x sub 4, negative or minus x sub 4. Why? Because the sign of the inequality here is greater than or equal. Okay? So when we have a greater than or equal sign, the slack variable will be negative 4. And you don't notice that we add a a sub 1 which is the artificial variable to offset the negative slack variable. Okay, so whenever we have a negative slack variable, we have to use an artificial variable to offset its negativity. Okay, negativity of the slack variable. So now let's go to uh, the iteration. So note x sub 4 is a negative because of the greater than or equal sign. In slack variable a sub 1 is added to start the simplex table. So negative m a sub 1 has a negative sign in the objective function because this is a maximization problem. So remember that. So back in our minimization problem, the slack variable or the artificial variable is positive in the objective function, while here in the maximization problem, we have our artificial variable as negative. Okay, so remember that. So in the simplex table, since x sub 3 and a sub 1 show matrix identity property, they are the first entering variables. So what whatever variables that shows the matrix identity property, we will use them as the first entering variables or our variables under x sub b. Okay, so they are the basic variables to start our iteration. Okay, so uh, again we will choose the highest positive value of cj minus zj, which is 10 plus 4m is the highest. So under x sub 1 column. Now we will solve for the theta. So the value of RHS is 5 here. So 5 divided by 1 is equals to 5. Next, the value of RHS here is 24. So 24 divided by 4 is 6. So the smallest positive value of theta is 5. So now we will replace x sub 3 by x sub 1. You notice in our second iteration, x sub 3 is replaced by x sub 1. Okay, so now, uh, what is the pivot element, or the element that lies in the intersection of the highest positive Cj minus Zj and the lowest positive value of theta? It is 1. Okay, so we will use 1. So we will divide all the elements in the previous row, which is x sub 3 in the first iteration, by it, the pivot element, which is 1. So we will write all the elements as is because it is 1. So now, what number we can use to make an identity matrix between x sub 1 and a sub 1, because they are the one that lies here in x sub b. Okay? So what number? So we can use the number 4. Okay? Why? Because when we use the number 4, so for the first column, x sub 1, 4 times 4 is 4. So the previous value of a sub 1 row is 4. So 4 minus 4 is equal to 0. Okay? So we can use 4. Next, for the column of x sub 2, 1 times 4 is 4. Okay? So 0 minus 4 is negative 4. Next, for the column of x sub 3, 1 times 4 is 4. Okay, so the previous value is 0. 0 minus 4 is negative 4. Next, 0 times 4 is 0. So negative 1 minus 0 is negative 1. Okay, for the column of a sub 1, so 4 times 0 is 0. So the previous value is 1. So 1 minus 0 is 1. Okay, so next, 5 times 4 is 20. So the previous value is 24. So 24 minus 20 is 4. Okay, now we will solve for the values of Cj minus Zj. Okay, so remember the 10 here is the numerical coefficient of x sub 1 column. Okay, under the 10 under C sub b, and negative m is the numerical coefficient of a sub 1 column, which is here negative m. So to compute for C sub j minus Zj values, we'll just multiply each. Okay, so 10 times 1 is 10. So negative m times 0 is 0. So 10, okay, minus 10 is equal to 0. Okay, so next, 10 times 1 is 10. Negative m times negative 4 is positive 4m. So 10 plus 4m is 4m plus 10. Okay, so now we will subtract it to 9. So 9 minus 4m plus 10. So it is equal to negative 1 minus 4m. Okay, or 4m minus 1. Okay, next, for the column x sub 3, 10 times 1 is 10. Okay, negative m times negative 4 is positive 4m. So we will add them. 10 plus 4m is 4m plus 10. Okay, so now we will subtract it from the value in the uppermost row, which is 0. So 0 minus 4m minus 10 is equal to negative 10 minus 4m, or negative 4m minus 10. Okay, next, 10 times 0 is 0. Negative n times negative 1 is positive m. So 0 plus positive m is m. Next, 0 minus m is negative m. And the last column, a sub 1, 10 times 0 is 0. Okay, so negative m times 1 is negative m. So 0 plus negative m is negative m. So negative m minus negative m is 0. Okay, and of course, for the RHS, we will not compute it because we have negative m here. Okay, so we'll just leave it as 3 dashes. Okay, so since all values of c sub j minus zj are either 0 or negative, okay, you notice that they are uh, either 0 or negative in our second iteration, there will be no entering variable. Thus, the algorithm terminates normally. So it terminates. If an artificial variable that is strictly positive, like a sub 1 is equal to 4, in the above table is included in the final solution, okay, so it is included in our final solution. It means that there is no solution at all for the problem, and this is called infeasibility. So remember that, okay? The following graph shows the solutions in the problem don't satisfy both constraints. Okay, so the problem, uh, our model don't satisfy the constraint. Okay, so this is the graph. So it shows infeasibility. Okay, so next, degeneracy. What is this? So example number 4, maximize z is equal to 3x sub 1 plus 9x sub 2, subject to x sub 1 plus 4x sub 2 less than or equal to 8, x sub 1 plus 2x sub 2 less than or equal to 4. And the non-negativity constraint x sub 1, x sub 2 is greater than or equal to 0. So adding the slack variables, we have the x sub 3 and x sub 4. So there's no problem uh, in their inequality symbol because they are all less than or equal. Okay, so the slack variables are positive. So for the first iteration, okay, we make our simplex table. So we use x sub 3 and x sub 4 because they form the identity matrix. Okay, so we will choose the highest positive value of cj minus zj, which is 9 under x sub 2. Then we will compute the theta. So 8 divided by 4 is 2. Next, 4 divided by 2 is 2. So here we have both uh, lowest positive value. So either of the two. Okay, we can choose either of the two. So in this, I choose x sub 3. Okay, x sub 3 to be replaced by x sub 2. Okay, so in our second iteration, you notice that x sub 3 is replaced by x sub 2. So now, what is the pivot element here? The pivot element, or the element that lies in the intersection of the highest cj minus zj and the lowest theta, is 4. Okay, so we will divide all the elements along the previous row, which is x sub 3 in the first iteration, by the pivot element, which is 4. So 1 divided by 4 is 1/4. So 4 divided by 4 is 1. 1 divided by 4 is 1/4. 0 divided by 4 is 0. 8 divided by 4 is 2. Okay, so we have to make an identity property for x sub 2 and x sub 4. So what number we can use? So we can use number 2 because in the column under x sub 2, when we multiply 2 by the value of the element along the row of x sub 2 is 1. So 1 divided by 1 times 2 is 2. So the previous element in x sub 4 row in the first iteration is 2. So 2 minus 2 is equal to 0. Okay, so number 2 will do. Okay, so in the first column under x sub 1, we multiply 1/4 with 2. So 1/4 times 2 is 1/2. So 1/2, the previous value is 1. Okay, 1 minus 1/2 is 1/2. Okay, so let's move on to x sub 3 column. 1/4 times 2 is 1/2. Okay, so the previous value is 0. So 0 minus 1/2 is negative 1/2. Next, 0 times 2 is 0. So the previous value is 1. So 1 minus 0 is 1. Okay, so 2 times 2 is 4. So the previous value is 4. So 4 minus 4 is 0. Okay, so we will now choose the highest positive value for our third iteration. The highest positive value here is the column x sub 1, which is 3/4. And we will compute now for the theta. So 2 divided by 1/4 is equal to 8. 0 divided by 1/2 is equal to 0. So now we will choose 0 because it is not negative and it is the smallest value of theta. Okay? So x sub 4 will be replaced by x sub 1. Okay? So our pivot element is 1/2. So we will just divide everything in the previous row with 1/2. So 1/2 divided by 1/2 is 1. 0 divided by 1/2 is 0. Negative 1/2. 1/2 divided by 1/2 is negative 1. 1 divided by 1/2 is 2. 0 divided by 1/2 is 0. Okay? Now we have to make an identity matrix again between x sub 2 and x sub 1. So what number we can use? So we can use 1/4. Okay? Because when we multiply the value of 1 under the column x sub 1 and the row x sub 1, which is 1, so 1 times 1/4 is 1/4. So the previous value in the previous row of the second iteration under along x sub 2 is 1/4. So 1/4 minus 1/4 is 0. Okay? So next, under the x sub 2 column, 0 times 1/4 is 0. Okay? So the previous value is 1. So 1 minus 0 is 1. Okay, so negative 1. So under the x sub 3 column, negative 1 times 1/4 is negative 1/4. Okay, so the previous value is 1/4. So 1/4 minus negative 1/4 is positive 1/2. Okay, so next, 2 times 1/4 is equal to 1/2. Okay, so the previous value is 0. So 0 minus 1/2 or 0 minus 1/2 is equal to negative 1/2. Okay, so next, 0 times 1/4 is equal to 0. So the previous value is 2. So 2 minus 0 is 2. Okay, so now we can compute for the optimal value because everything here in the cj minus zj is 0 and negative. So the optimal value is 18. So now, since all values of cj minus zj are either 0 or negative, there will be no entering variable. Thus, the algorithm terminates normally. Notice the repetition of the solution and the optimal value from second iteration to the third iteration. So you notice this repetition, okay? So 2 and 0, and 2 and 0, and 18 are repeated, okay? This implies that the model has at least one redundant constraint, okay? In this case, so it has a redundant constraint when you when we encounter that repetition. So the first constraint as shown by the following graph. So this is the first constraint shown by the following graph. So as you notice, we have a redundantness of the solution. Okay? So this is the redundantness. Now let's go to 4.6 Alternative Optima. So 4.6 Alternative Optima. So example number 5. Maximize z is equal to 2x sub 1 plus 4x sub 2. Subject to x sub 1 plus 2x sub 2 less than or equal to 5. X sub 1 plus x sub 2 less than or equal to 4. With the non-negativity constraint, x sub 1, x sub 2. So this should be greater than or equal, okay, to 0. So a typo error. Okay, note that our non-negativity constraint always comes with greater than or equal. Okay. So adding slack variables. So all the slack variables are positive. Okay, because all the symbols in the constraint are less than or equal. So we now go to our iteration, simplex table. So we plot everything, then we start with x sub 3 and x sub 4 because they have the identity matrix. Okay, so we choose the highest positive value of cj minus zj, which is 4. So it is in the column of x sub 2. Now we will compute for the theta. So the values of RHS here, so 5 divided by 2 is equal to 5 halves or 2.5. Next, 4 divided by 1 is equal to 4. Okay, so the lowest positive value in the theta is 2.5, which lies along x sub 3 row. Thus, x sub 3 will be replaced by x sub 2. Okay, so how do we replace it again? We will just divide everything in the column, the previous column with, in the previous row by the pivot element. So what is the pivot element? The pivot element or the intersection is 2. Okay, so 1 divided by 2 is 1 half. So 2 divided by 2 is 1. 1 divided by 2 is 1 half. 0 divided by 2 is 0. 5 divided by 2 is 5 halves. Okay, so next, we will make an identity matrix between x sub 2 and x sub 4. So what number we can use? So we can use value of 1, okay, because under x sub 2, when we multiply 1 by 1, okay, it is 1. So the previous value of row x sub 4 is 1. So 1 minus 1 is 0. Okay, so in the first column under x sub 1, we multiply 1 half by 1, which is will be equal to 1 half. So the previous value is 1. So 1 minus 1 half is 1 half. Okay, now let's move on to the x sub 3 column. So the value of the row x sub 2 is 1 half. So 1 half times 1 is 1 half. So the previous value is 0. So 0 minus 1 half is negative 1 half. Next, 0 times 1 is 0. So the previous value is 1. 1 minus 0 is 1. Okay? So next, 5 halves times 1 is equal to 5 halves. So 4 minus 5 halves is equal to 3 halves. Okay? So now, we will choose the highest positive value, which is 3/4. It is under x sub 1 column. Okay? And now we will compute for the theta. So 5 halves divided by 1 halves is equal to 2. 3 halves divided by 1 halves is equal to 3. So the lowest positive value of theta is 2. So x sub 2 will be replaced by x sub 1. Okay? So we will just, for the third iteration, we divide all the elements in the previous row of x sub 2, which is in the second iteration, by the pivot element. So the pivot element here is 1 half. Okay? So 1 half divided by 1 half is 1. Okay? 1 divided by 1 half is 2. 1 half divided by 1 half is 1. 0 divided by 1 half is 0. 5 halves divided by 1 half is 2. Is 5. Okay? It is 5. So next, uh, for x sub 1 and x sub 4, we have to make an identity matrix. So what number we can use? So we can use 1 half, okay, to have an identity matrix. Because when we multiply 1 by 1 half, okay, is under x sub 1 column, we have 1 half. So the previous value is 1 half. The previous value in the x sub 4, second iteration, is 1 half. So 1 half minus 1 half is 0. Okay? So next, for the column x sub 2, 2 times 1 half is 1. So the previous value is 0. So 0 minus 1 is negative 1. Okay? So next, 1 times 1 half is equal to 1 half. Okay? So the previous value is negative 1 half. So negative 1 half minus 1 half is equal to negative 1. Okay? So next, 0 times 1 half is equal to 0. So the previous value is 1. So 1 minus 0 is 1. Next, 5 times 1 half is equal to 5 halves. So the previous value is 3 halves. So 3 halves minus 5 halves is equal to negative 1. Okay? Now, since all the Cj minus Zj values are 0 and negative, we can compute for the optimal value. Okay? Because it will not increase anymore. So 2 times 5 is 10. So we will not compute this one, negative 1, because it is infeasible there. Okay, so 2 times 5 is 10. So our optimal value is 10 here. Okay, so since all the Cj minus Zj are either 0 or negative, there will be no entering variable. Thus, the algorithm terminates normally. Notice that the optimal value in the second iteration and the third iteration is the same. So it is the same, okay? It is both 10. This result to alternative optimal solution. Point B and point C as shown in this graph. So you notice that this point B and point C are both optimal solution. They are, so we call this condition as alternative optima. Okay. Now let's go to the 5.0 Excel solver method. So open your Microsoft Excel. So once you open your Microsoft Excel, you go to File. Okay, this is how to add Excel solver in your Microsoft Excel. Okay, so you go to the options. So after going to option, you go to add-ins. So in the manage, you select Excel add-ins, then click go. Now in this box, you will select solver add-in. Okay, solver add-in. So you will just click OK. So when you click that, you notice that uh, under the data, so you will click data, okay? Under the data, you have your solver option, okay? So it should appear there, appear there, the solver option, okay? So let's go now to this problem. This is the example number 1 problem, the maximization. Okay? To illustrate it more clearer, we shall go to this Excel solver, okay? So first, we will click data, then click solver. Okay, so here in the solver, you will put in the objective function set objective the value of the optimal C. Okay, you will just click. Okay, then you will click maximum. Okay, because we are maximizing here. Then for the by changing cell, you can click that, and you can highlight this, the cells under vaccine 1 and vaccine 2. Okay, then click that again. Then for the subject to constraints, first let's just remove them. Okay, so let's reset. Okay, so there no. So we will put the subject to constraints here. Okay, so we will click add. So clicking cell reference. So in the cell reference, we will first select uh, the cell under use machine hours, which is this. Okay, then we will make uh, the sign less than or equal, because it is the sign of our constraints for machine 1 or the constraint 1. Then for the constraint, we will select this, the 21 under available machine hours. Okay, so we will just click add. Okay, and for the next constraint, the constraint 2. Okay, so for the minimization, okay, from the example number 2, okay, the problem about making modules, okay, so it is a minimization. So this is how you do it. Okay, so the formula of the cell under optimal Z is this. You will just get uh, the product of this cell and the cell, and you add it to the product of this cell and the cell. Okay, next, the formula of this cell under accomplished target is you get the product of this cell and the cell, and you add it to the product of this cell and the cell. Okay, lastly, the formula of this cell, you will get the product of this cell and this cell, and you will add it to the product of this cell and this cell. Okay, now we are ready to use the Excel solver method. So data, then click solver. Okay, for the set objective, you select this and select the cell under optimal Z. Okay, so it is selected. So select min. Select min because we are minimizing here. Okay? And under by changing variable cells, select this. And select the cells under G1 and G2. Okay? So they are selected. And subject to constraints, we delete this for illustration purposes. Okay? Then we should click add. Then for the first cell reference, click the cell under accomplished target for the constraint 1. Then select the symbol for constraint 1. The symbol for constraint 1 is greater than or equal. Okay? Then for the corresponding target modules per week is 4. Okay? Then click add. Then for the second cell reference, click this. Okay? And the sign for the second constraint is greater than or equal also. Okay? And the corresponding target modules per week is 10. Okay? Since this is the last constraint, you can click OK. So you notice they are added in the under the subject to constraints. Then again, make sure that this box make unconstrained variables negative to be checked because we don't want negative results. Then you click Simplex LP because it is the one we are using. Then click solve. So a window like this will pop up and just click OK. So there you have it. Your solution 4 and 0 and your optimal value of 20,000. Okay?